Hello everyone, I'm here today to talk to you about the Clang tools. So what I'm sort of focusing on here is not Clang itself as a compiler, it's sort of more the sort of things that are surrounding Clang, so it's all of the sort of extra tools that you can get around in that bit. I'm also going to briefly look at the sort of how you might use the developer tools, as in build your own tools using the libraries that Clang provides. Now obviously I'm not going to have a lot of time to go into a huge amount of detail with that, but what I will do is let you know how to get started, try and help you to not fall down some of the pitfalls that I fell down when I first started to look into this type of stuff, and then go ahead from there. Okay. So expanding on about that, so Clang was actually designed to be much more than just a C and C++ compiler. So one of the big problems of the C++ ecosystem, certainly 5 to 10 years ago, was that there wasn't actually any good IDE support, refactoring tool support. And one of the main reasons for this is just that C and C++, well, C is fairly easy to parse, but C++ is very, very difficult to parse. There have been several attempts at it in the past. A lot of them kind of did just enough for what they needed, but not enough to be accurate enough to do things like actually refactor and change source code. So Clang was designed as a sort of bunch of libraries, so that they could abstract away some of this facility so that other tools could be built out of the libraries that sort of do the C++ parsing. And these all work on the abstract syntax tree, the AST. And as well as providing you with these libraries to do some of this building your own tools, there are some pre-built tools as well. I'll do a very, very brief introduction to some of them and some of the ways that I found most useful. So, first thing I'm going to do is the easy bits, which is just going to look at some of the sort of built-in Clang tools. So starting with clang-format, which is a very, very simple sort of code formatter, static analyzer, so this is a sort of static analysis tool, kind of like something like Coverity. Clang-tidy is a refactoring tool type thing where it will analyze your code, tell you what bits that potentially can be changed depending on various coding standards and the like. Okay. So clang-format is the easiest one to describe, and it's also probably the one that's easiest to pick up. It's also the one that I was most skeptical about when I first heard about it. You hear people say, well, okay, you just use code formatting tools, they're great. And then you think, well, really? Are they really that much better? I mean, my editor I can just tab and it'll indent things for me, and why do I need a formatting tool? So basically what clang-format specializes in is incorporating all the latest algorithms for breaking code into a specific 80-column layout, and it does a pretty good job when you've got, say, large macros, functions with large amounts of parameters, large strings. It will do a pretty good job of actually putting a layout that's probably better than you could do yourself, and it means that when you edit things you don't have to reline everything up. So there are plugins for Vim, Emacs, for example, where you can just select a region of text and just apply clang-format to it, and it will instantly snap back. So I found this to be, quite a big productivity enhancement, because I've stopped bothering to indent, to manually indent a lot of the code. I just type it out and then just go select rectangle, go format it, and it's all done. And I'd say it's actually good enough that you can actually use it as a basis for a coding standard in the project, where you basically say you get rid of arguments over formatting by just say run clang-format over it, that type of thing. So that's what they do with LLD. So as standard it uses the LLVM coding style, but you can change it to the Google, Chromium, WebKit and GNU coding style. So I'll give you an example of how this looks. So here is an entry into the International Obfuscated C programming competition. So we can see what clang-format will do to that. Now it won't look as pretty as that, but let's just see if clang-format can actually put it to something that you might almost be able to look at some of the structure for. So sorry about the small size font, but you can see at least what it's been trying to do. So it has had a macro up there that's it's managed to break into something that looks like a sort of a block. it's picked out a loop there. It's made sure that the string's all broken in the same column, that type of thing. It's again pulled out some of the expressions, labelled the conditionals up, that type of thing. So it does a better job on non-international obfuscated C competition, but just give you the sort of perspective, it can actually take some completely unformatted code and put it into order. And to give you an example of one thing I wrote in a personal project, I wrote a code generator for something, and instead, typically with code generators, they spit everything out on one line or complete mess, and all you have to do is pipe it to clang-format, and you can get something you can actually read at the end of it. Anyway, that's clang-format. Okay, before I move on to the next one, I just want to introduce the concept of a compilation database. So one of the things that you'll find if you're doing any kind of processing on C and C++, is that the preprocessor can significantly affect what's going on. So things like if you put define something before or after, you can actually modify what's in there. You've got various includes, that type of thing. And if you've got a large program with, say, thousands of source files, specifying all of the includes and extra defines that you need to pass on a 1,000, 2,000 source file project becomes exceedingly tedious over the time, almost to the point of you making you not want to bother applying the tool again. So what Clang does is it uses something called a compilation database, which effectively just saves the options that you use to build the project. It's very, very simple JSON database. I won't bother going into it. It's human readable. You can just open it and it will make sense. Now, obviously, you don't want to make one of these by hand for your 1,000 object file project. So this is actually, there are some tools made to build this directly. For those using CMake, for example, LLVM and Clang, just add the extra defined CMake export compile commands. Ninja has support built in for this. And then there is another tool called, I don't know how you would pronounce it. The word is bear, but it stands for build system ear. So whether it would be beer, I don't know. But anyhow, the idea for this is that you will put it in front of a makefile. So you could get that on GitHub. So if you've just got a makefile-based project, you can get a compilation database out of that. Okay. So moving on to the Clang static analyzer. So this is the reason clang-format doesn't need that to just format text. But something like the static analyzer really does need to know exactly what the compilation options we use to compile the project. So you pretty much have to use a compilation database to make this work. So I'd have to say one little caveat for the Clang static analyzer: it is not going to be able to perform magic on your project. It's probably not going to be as good as a commercial tool such as Coverity. Some sort of interesting findings that we've done whilst experimenting with these things, we find that almost every static analyzer finds a completely disjoint set of problems and has another completely disjoint set of false positives. My understanding with the Clang static analyzer is it does a better job with C than it does complex C++. And at the moment, I think there's experimental support for inter-translation unit references, but it does a much better job on single source files. How you would run this is you just use scan build before your sort of CMake file step or make file step, and it will produce the output for you. So I've got an example here. I've got a very, very trivial program here. I won't ask, just for the time, I won't ask the volunteers to spot what the problem is in there. But we can just about, I'll probably have to read this out, but after I ran scan build over there, second function call argument is an initialized value, line 7, column 5. Got that here. And it then goes through and shows you the steps of how it deduced that the actual program was incorrect. So that can be quite valuable if it does actually find a bug. Although you could say these are fairly trivial type of bugs, sometimes they can bite you, particularly if you've not got a test case that goes over them. Okay. Finally, on to clang-tidy. So this is a lint-like tool, predominantly, I guess, for the main sort of default checkers that are on here are again sort of basic style guides. You can add some sort of optional ones, such as the C++ core guidelines, the Google style guidelines, that type of thing. It can suggest fixes for certain classes of these problems. For example, there's a modernize one where it can say, I see you're using C++ 98 code base. If you were using C++ 11, here are some simple transformations you could do. Say something, for example, replacing null with null putter, that type of thing. And it can do those edits for you, or can produce a patch for you. So here's another simple example that I put here. So this is just a standard for loop that you would see in C++ 98. And I've run clang-tidy on it with the modernize check saying, please can you modernize my program using C++ 11. So we see here what it said to me, redundant void arg. Well, not really necessarily a bug, but I could remove that. Use range for loop instead of the full thing here. So we would replace all of that with just that bit of green text there, the range for. And then it's got, this one is actually quite interesting in that I could in C++ 11 use auto for that huge type there, and that would also be a cleanup. But it's also saying there, fix will not be applied because it overlaps with the better fix, which was just use the range for loop. So if you've got an old code base and you're looking to move to C++ 11, then it might be worth running that, and it might be able to pick a few trivial things out for you. Okay, so I'm past the simple stuff now. Here's where it starts getting a little bit more complicated. So this is where you take some of the libraries that the Clang distributions provide, and sort of this is when you can start building some of your own tools. So just a quick word about the sort of structure of Clang here. So the first thing, I won't bother reading out all of those. That's just showing the sort of library structure of Clang and how they've designed it so that you can separate out the parsing and the analysis from the actual generation of code. And what the actual libraries have provided, or how you actually use these libraries to make your own tools, is via one of three choices. So you've got libclang, which is a sort of, let's say, a stable-ish high-level C interface to Clang. So what they've done here is they've produced a sort of facade interface onto Clang. You can't do everything that you can in C++, but it's a sort of an interface they try and keep stable over releases. So if you want to build a program once and then only make minimal changes against it when the Clang is updated, then that's generally the best way to go. It's also probably the simplest interface to understand. Libtooling is basically the direct C++ interface that Clang uses itself, and of course that's modifying and changing all the time. Plugins use the same interface as libtooling, but plugins are basically run when you do compilation itself. I'll go into a little bit about why you might want to use each one on the next slide. So libclang is, I guess, essentially designed for doing IDE. Well, if you're an IDE maker and you want to be able to parse C++ and do things like syntax highlighting or whatever, or grab keywords out of it. So because you can't do everything, it's not recommended for everything. But if all you want to do is just look up tokens, find their source location, jump to them, that type of thing, libclang is probably the best choice there. There's also Python bindings available, which is what I'm going to talk about towards the end of the presentation. So I'd also say that libclang isn't really suitable for modification. So if you're writing a refactoring tool, probably not the way to go there. So a plugin is a sort of shared library that Clang runs on compile. So this is sort of thing as, say for example you had a code base where you were going to prevent any uses of the variable name foo because say you got frustrated all your developers using silly variable names or something like that. So you could write a Clang plugin that would scan for all the variable definitions called foo and then give an error message at that point and stop the compilation. So this is the sort of thing you would then tend to run a plugin is if you wanted to halt compilation if you found something in particular. Typically you probably want to write your tools so that it ran not at compile time, so you could just run it on the whole code base at a time rather than having to recompile everything at that particular point. And that uses the same C++ interface as the actual Clang itself uses. Libtooling, this is the sort of thing that you tend to write refactoring tools in, and this again uses the same C++ interface as the AST. Now, why do I say that the C++ interface is unstable and the C interface is stable? It's basically because the Clang project tends to prefer refactoring over stability between releases. So it will basically say if you want to use the latest Clang, you've got to keep your tool up to date, that sort of thing. So if you want to build a tool and keep it going over time, you've got to be prepared to keep upgrading the tool to match Clang API changes, that type of thing. And you've got a much better chance of doing that without large source modifications if you stick to the sort of stable C interface. So before you start going into this, a little bit of a word of warning. So what I found, you'll find large amounts of sort of blog posts of using libclang on the internet, that type of thing. It sort of makes it sound like it's, oh, I can just go and do this in an hour or something like that. It's not quite that simple, unless you want to do something very simple. And you'll also find, well, basically what you'll find is that on almost all the tutorials online, they basically do a scan of the abstract syntax tree, finding one particular type of node, and they'll print out something about that one particular type of node. They won't actually do anything that means, oh, how about correlating that one node with some other bits of the source tree, or saying, let's do something only for this one particular type of function. Once you start going out into anything above one node, you have to then start knowing bits about the structure of the Clang AST, and you have to start building bits of your own framework around that. So the first thing I'd say is make sure you have a very clear idea of what you want to do. I first sort of started, thinking, oh, let's build something for this talk. And it's like, well, what? Exactly. And I sort of found that I had to sort of deliberately set myself a task where I knew exactly what I wanted to look for. And then, only then could I actually work out what the best way out of all of these multiple ways of doing things was actually the thing that I needed to do. The documentation follows, I guess you call Clang LLVM standards, and is extremely sparse. The documentation is effectively the source code and various blog posts that you can find online of people doing examples, the Clang examples. So if you go into this, expect to have to dive into the source code to find out what's going on. And there are comments in there, there are sort of useful sort of references, it's not impossible, but yeah, don't expect clear documentation here. And the examples that you can find online, usually quite good to get you started, but if you're wanting to do anything particularly complicated, expect to have to dig into the details. And I did find that the Python bindings, whilst very convenient, it may be just my lack of knowledge with Python, didn't scale as well. I certainly tried to run my program on Clang itself and it ran out of memory, so it may not be the best thing for big code bases. Okay, so we'll start with libclang. So I'm going to spend most of the time talking about libclang here. I'm not going to talk about libtooling in any great detail because it's just too big. So what we've got here is what's called a cursor-based interface to the abstract syntax tree. So the cursor is effectively saying this can be any one of the Clang AST nodes. So what you'll do is you'll have a cursor that starts at the top of the AST, and you'll basically walk the AST saying start at the top, get the children, traverse to each child, get the type of node, traverse to each child, get each type of node. And you basically you either sort of run a visitor and sort of with a callback on each node, or in the Python API, you basically say get children and walk across each of the children. So the Python API has a sort of more Pythonic interface, which is the sort of getting an iterator over the children, and you walk over that. So what I sort of thought for my particular example here, I wanted to print out a histogram or bar chart of the number of function parameters in a project. So I wanted to know how many, just on average, am I using a very small number of function parameters to my functions? Am I using a very large amount? I started to think, do I include C++ lambda expressions? I started with that and quickly got into trouble because Lambda expressions in the clang AST are a little bit complicated, and I couldn't fit it into a very simple program, and I just had to cut it short at that particular point. So what did I need for this? I needed the libclang.so shared library. So this is just a binary distribution here. I needed the Python bindings for a file called cindex. I've put the location of the file there if you want to go find it. So again, I found a lot of what I needed to do just by looking at that Python file and finding out what functions that I needed to call. There isn't really any explicit documentation for it. And then you need to set the various environment variables so that you put the cindex on your Python path and the libclang.so in your sort of LD library path. Okay. So the first bit of Python, and this is just kind of, you're probably not going to be able to read this, but I've put it here so that if anybody is interested and they want to go after the thing, they can pick up the slides and go through looking it through. But effectively, this is the sort of thing that you would write as your sort of main function in Clang to basically use a compilation database. So what they've done in Clang is they provided some functions to parse all of the compiled database for you, so you don't have to write that from scratch. So all I'm doing there is finding the compile commands.json file, passing it into the sort of compdb get all of the commands, and then I'm just iterating over each of the commands, and then running my visit node function, which I'll go to on the next slide. So yeah, there's just some things here. There was a few things that when I first got here, I've put some sort of comments where the function was expecting an iterator and this various thing was giving me a string and I had to do some kind of transformation on it. That will just save you a few minutes, but I won't go into any of the details in there. Okay, so here's my visit node, very, very simple. Function decal, CXX method, that's just saying, am I a normal function, am I a C++ function, and is definition. That was important, and that's also one of the caveats that I came across in that initially when I started with Clang, I used the parse, I said don't parse function bodies because I wasn't interested, I was only interested in the number of parameters, but it turned out that I had to use isDefinition, I had to use the parse the whole body in order for isDefinition to work. Why am I using isDefinition? Well, basically, if you say get the number of parameters in a function, how do I know that I'm using a declaration in a header file or the actual thing? And I found that's actually one of the things in a big project that you'll have to come across. You're going to have to be careful with, duplicates, that type of thing. And I'm basically just recording the parameter, and I wrote some code to make sure duplicate the locations. Which I won't go into any of the sort of details of here, but yeah, just some of the complications that I went through here. So analysing a whole program, takes a bit of care. You've got to be sure that you're actually looking at a definition and not a declaration. The header files will be included multiple times throughout the whole project. Make sure that you count them only once. Yeah, there's something that I wish I knew to start with. It was the cursor.getUSR function, because to start with I wrote my own matching across source locations, and then it turned out that there was a function that did it all for me that I just didn't know existed until later. Lambda functions are difficult to handle, don't worry about that. That's if you aren't doing anything there. And parsing is slow with the Python interface. It was taking as long to compile as Clang was taking to compile. So you probably want to stick to C++ for that. Okay, and here's the answer. Hooray! One of the advantages of using Python is that you can just use matplotlib and things like that to just get the data and just splat it into analysis very, very quickly. Okay, so I won't go into this too much detail because we haven't got much time left. I've got about a minute. So libtooling, there's two ways that if you ever go into here, you'll see two ways of looking at things. There's something called a recursive AST visitor. That's kind of how Clang itself is written. And then there's something called an AST matcher. Now, AST matcher is kind of like a domain-specific language that they've written to apply little sort of things like isDefinition and whatever. And there's a tool called clang-query where you can basically interactively test to see how you can make up your actual matches. So I wrote an equivalent version of C++ of the thing in libtooling. I didn't put it here because it's a bit big, but it was a similar size to the Clang program. It was a bit more conceptually difficult to understand, but I think myself being more familiar with C++ than Python, I would probably start with libtooling rather than use Python. I think it was just a more direct thing. The sort of AST matches were actually more useful for me. So what I've done here, put some references here. These slides obviously will be up on the Linaro thing before. This is where the things that I found the most useful to go and find out about how these things here. There's some excellent tutorials, particularly by Eli Bandersky, who's very, very nicely put some a GitHub page up that he maintains once every 6 months to keep it up to date with the latest Clang. I did have to add a couple of libraries to the one when I compiled against tip of trunk, but that wasn't too difficult to work out. Okay, and there's some extra references from libtooling. Okay, so just to conclude, so Clang's got many of extra tools that you can make use of, even if you're using GCC. Building your own tool is practical, but it's non-trivial. Expect to be conflicted by so many different choices, it'll take you a while to settle down there. I say that's probably about all I should go for there. So we're technically out of time, so if you want to leave, but if you want to come and ask me questions, I'm quite happy to stay for a bit. There isn't anything after this, I don't think, so I'm quite happy to take some questions.
Hi. So you're mentioning the compilation database and the problem with header files. Yeah. So I use a thing called irony mode, which is a code completion engine for Emacs, and that's built with libclang. Yeah. But whenever I edit a header file, it doesn't work because it can't find an entry in the compilation database.
Oh, right, okay, yeah.
It needs the entry in the compilation database so it can build the completions. So has there any thought been given to any potential solutions for that?
I think, as far as I know, there was a guy, I think it's Attila Neves, who's written something about something like CMake IDE, where it basically is a background process that looks for changes that might, and basically does a recompilation of the CMake file in the background. I think this is typically meant for the IDE problem. I don't think there's an easy solution other than manually forcing the rebuild to update the compilation database. I think typically, if you're going to run one of the tool over a large code base, I think it's probably not too difficult to just rebuild and then use that database. But yeah, I don't think there's a good incremental update story. You can manually update it, but
there's no entry in the compilation database for a header file on its own, because header files are part of the C compilation units. But I guess you'd need to do something like scan every object file that was built with that header and see if there's a common set of
I'd say that I think that was one that they'll probably say it's an IDE problem rather than the Clang problem. But yeah.
Okay.
Okay. So no more questions. Then thank you very much.